Okay, off we go. So here's where we were last time. We were talking about change of variables. And, so remember the big idea of change of variables, it's basically a ripoff of the substitution rule from single variable calculus. So which makes for a nice segue, but let's just sort of recall the double integral point of view. We're entertaining the scenario where we have a double integral computed over some domain, presumably somewhat undesirable in at least some sense. And we want to rewrite this as an integral, a different integral over a different domain for convenience of computation. The big first step is to figure out some way to view your domain as being an image of something better. Perhaps, for example, a rectangle like this. And we'll see a bunch of different examples in the next few minutes. So if you can view your undesirable domain as an image, then you can do what we call a pullback. And the idea of a pullback is that when everything on the right can be expressed as some formula in terms of stuff on the left, then you just plug in, right? And that will then turn that undesirable integral on the right into a much more desirable integral on the left with a key point, much more desirable domain. Okay, now what's the benefit of this? Well, why is it so important to have a desirable domain? Well, just think about how you'd compute this integral on this wacky domain. And I think whichever way you slice, you'll notice you're going to hit corners, multiple corners, and other problems are going to arise. And so this is going to be several iterated integrals to compute with, and nobody wants that, right? All else being equal if we can avoid it. So turning it into an integral over a rectangle means not only is it going to be a single iterated integral, but it's going to be a single iterated integral with easy bounds, which will make for easy single variable integrals. Hopefully, fingers crossed. That's the strategy anyway. Okay, so we talked about the stretching factor. The big idea of the stretching factor is that little pieces of area on the left have images that are little pieces of area on the right, but they're not the same size. Why would they be? This change of variables function g stretches things out and turns things around and contorts and distorts. We have no reason to think they should be the same size. This stretching factor, we have a formula for it. A couple different ways to think about it. This is a little bit more of an explicit formula. It's the absolute value of the determinant of the derivative matrix. Nice and crisp, nice and rolls off the tongue very nicely, right? Another way to think of this stretching factor, computationally kind of more convenient notation, one could argue, is that you can rewrite the determinant part of that as what appears to be a fraction. Very importantly, it's not a fraction, right? But we use a fraction notation for kind of convenience, right? Okay, all right, so this is all kind of abstract setup that we talked about last time. Let's get our hands dirty and do one. Here it is, example on the next page here. We're going to look at this domain here, which is a weird domain. And easy observation, imagine how you would slice this up, dx, dy, dy, dx. Take your pick, you're going to hit two corners. This is going to be three separate iterated integrals. Ugh. Right, so let's just hope we can find a better way to solve this problem. So that, notice it is given as an image. It's given explicitly as an image by way of this function. And furthermore, that function is given. Now, this is just a getting started example, right? So, in general, will you have the change of variables function given to you? Probably not. Sometimes. But anyway, let's get the mechanics down first, and then we'll talk about how to make good choices on change of variables functions. Okay, so it is an image. Specifically, it is an image of the unit square. Right? So when we do our pullback here with this setup, as set up as it is. The pullback is going to take an integral on this undesirable domain and turn it into an integral on this much better domain there. Okay. All right. So now to do so, reminding ourselves of our formula here, we're going to need to compute the stretching factor. After all, that's what's going to go inside of the integrand of my new integral to account for the fact that I'm changing domains. Little pieces of size are not the same on the left side and the right side of this picture, right? So we are going to have to compute that. Remember, here's notation and formula for how we're going to compute that. And following that rule, nothing to it. You take your formulas for x and y, and by the way, please do keep track. X, being the first output variable, is the first coordinate of your change of variables function. So there's your formula for x right there. Right? And likewise, y is the second output from your change of variables function. So there's its formula right there. Compute the appropriate partials and assemble, and your determinant, your Jacobian determinant, is this formula right here, which we need to compute an absolute value of. And how are we going to get rid of those absolute values becomes the next question. How are we doing so far? Is everybody with me so far? Okay, so how do we figure the absolute value? Can I just leave the absolute values in the integral? That would be terrible, right? If we have an integral that has absolute values in it, we don't have any formulas for how to integrate stuff with absolute values in it. We would have to break it up into separate pieces of where is it positive, where is it negative. So let's get that part done first. I claim, good news, that this expression here, in the scenario that we're given, I claim that that is always negative. Now, this is not immediately obvious. You can't just go around declaring stuff, right? So how do I know this is negative? If I assert that this is negative, how do I know? Well, you'll recall that the integral that I'm going to be doing is an integral, my new integral, is over this square, unit square. And keep in mind that's on the UV plane, and so I can see right here on the U-axis what the range of values of U is going to be. U, this thing right here, is clearly always between 0 and 1, right there in the picture. Everybody see that? Okay. And then likewise, V, that thing right there, well, I can see right here in the picture. There's the V-axis. I can see right there, V, also always between 0 and 1. And now, casual glance at our formula. I have 4 times something small times something else small. Minus 9, right? There's no way that's ever going to be positive. Is that cool? Okay. All right. So, this being as it is always negative, its absolute value is the negative of itself. That's, once you see it, perfectly obvious, but you do have to kind of think that through to persuade yourself. And if you're not clear on how I did this, come to office hours. We'll talk about it. Okay. All right, so we're basically done here. Now it's just a matter of kind of plugging everything in. Let's see here. We've got our little pieces of area over here, dx, dy, that are stretching factor times du, dv. We just computed our stretching factor. Our stretching factor is that formula, which I stick in right there as it's supposed to be. Now the only thing remaining is the question of how do I figure out what is x plus y, right? I mean, this expression right here, x plus y, how do I rewrite all of that in terms of u's and v's? And again, reminder, don't forget, we have an explicit formula for x. Being as it is the second output coordinate, its formula is the second output formula in the change of variables function. It's kind of easy to lose track of that, but makes it very helpful to rewrite x. And then likewise y similarly. So altogether, x plus y then is that right there. Everybody happy? Okay, so now let's take stock. Is this a win or a loss? I could have just computed this integral right here. By contrast, I seem to have negotiated that instead I could compute this integral right here. And at a quick, careless glance, you'd look at the new formula and think, wow, that looks a lot worse. Look at all those terms. And it's quartic, right? Seems like a lot worse than just x plus y up there. But keep in mind, the integrand is not the problem. The problem is the domain. And that original integral up here is computed over a weirdo domain with corners and such, and that's going to be 3 separate iterated integrals, whereas this new integral is computed over the unit square, about the best possible domain you could imagine. Right? It's a rectangle, constant bounds of the world's easiest numbers, 0 and 1. That's the dream, right? And so even though the expression's a little harder, I have a strong preference for this new integral. By the way, I mean, you can make the case, well, the integrand's harder. If it's still a polynomial, it's still easy, right? Way better than what we have on the right there. Which, again, not only would this be 3 separate integrals, but the bounds for that have a bunch of algebra in them. In order to find the bounds for those the 3 separate purple integrals I'd have to write down, I would need to find an algebraic relationship between x and y. And the way this is given, it's not even immediately clear how I would find a convenient algebraic relationship between x and y there. So the purple approach is not friendly looking. And so this is a big win. Everybody on board? Buying it? Okay. So, how do you find change of variables functions? And there's various different scenarios, and y'all have heard me say a million times, and you're going to hear me say it a million more, that the useful metaphor here is tools in a toolbox, right? So there is no single way to do it, but there are various tricks that are useful in various cases, and I'm going to show you a bunch of these tricks. So here's a short list of some change of variables functions that can be useful in different circumstances. If you want to move something around, well, we have an easy formula for how to take points and sort of move them around. Just, you always want to keep in mind that what a given formula does in the pullback process is kind of the opposite. So reminder, looking at the picture, our change of variables function goes that way. In the pullback, we're kind of going the other way, right? So whatever G does, pulling back will kind of undo that. And so with that in mind, if you have a change of variables function, for example, that it would seem is adding the vector a comma b, in the pullback, that will translate backwards. In other words, it will subtract the vector a comma b, etc. for these other examples. So let's see one in action. This is a nice question. A very common scenario, by the way, that you have a domain that looks fine, except it's at an angle, and wouldn't it be nice if we could just kind of rotate it? So here we go. Let's look at this domain right here, described in the statement of the question. So it's a square. I like squares, right? But it's tilted. And so if I were to slice this up, again, the old-fashioned way, I'm going to hit corners here and here, for example, if I slice like so, and then I'm going to hit the other corners if I slice the other way. So this is, as is, actually a pretty undesirable domain. Okay. All right. So wouldn't it be nice if I could just rotate it a little bit? And so the observation to make is that this is a rotation of something else. And just for sort of color convenience, the square that we have is a rotation of what I'm going to call the square over here, like this, which just for sort of geometric convenience, let me draw sort of a little outline of it, like that. So we're looking at something that is a rotation of something else. Let me say that differently. We have now conceived of this undesirable domain as being an image. It is the result of applying a change of variables function to a different domain that I like better. And so when I do the pullback, what's the pullback going to do? The pullback turns this into that, or, if you will, a little bit easier to visualize, it rotates my domain, in some sense, it kind of rotates it clockwise. There's that undoing that I was talking about. Does that make sense to everybody? Okay. So, with that, let's try to understand this change of variables function. Now, it's a rotation. Counterclockwise rotation. I hope you all remember. So there's some linear algebra that we're going to be using a lot in this class. Don't forget, linear algebra is prereq for this course, right? So I'm assuming you're good to go on the following. I'm going to say it very fast, just as to give you the checkpoints that I need to make sure that you're good with. But the way we understand this rotation is first to recognize that all rotations are linear transformations. Rotations around the origin, that is. Linear transformations can always be represented with matrices. Matrices can be understood by their columns that are the images of the standard basis vectors. And so what you need to do is take this rotation, the idea of a counterclockwise rotation by some angle theta, think about what that does explicitly to standard basis vectors, write down those images, those are your columns. And if you do that, then what you will get as a result is this matrix. Now, again, make sure you can do that. If you're not entirely clear on that, no problem. Come to office hours. I'll walk you through it. No problem. We'll straighten this all out, right? But please do come to office hours so that I can help you with that. Okay, so now we look at the particulars of this question, and specifically, let's notice that this point right here is that right there, and that gets my foot in the door, and I can see what the angle is. The amount that I am rotating around the origin is pi over 6, a little trig. Reminder, trig's in the prerequisite trail. I'm assuming y'all are all rock solid with trig, right? So make sure you're good with that. So knowing that the angle is pi over 6, the matrix turns into just that. And so here is our explicit formula for our change of variables function. Our counterclockwise rotation is computed by that formula right there. Okay. All right, now it's all over. Premature celebration. We do have to compute the Jacobian determinant, aka this thing right here. Notice I hesitate to call this the stretching factor. The stretching factor is actually the absolute value of that. It's really easy to forget that absolute values. Please be careful, right? So we'll just compute without the absolute values first and then deal with that later. Here is the resulting determinant to be computed. You want to make sure you check those details. Make sure you know where those numbers came from. Right. Keep in mind those are the partials of x and y with respect to u and v. Wait a minute, where's my formula for x? Right, where is x? Oh, here it is, though. There's x. X is this dot product right there. Is that cool? Yeah. Okay, this determinant easily computed. You get one happy little conclusion there. Isn't that nice? What are the odds? The more you think about it, it's actually pretty clear. In fact, we already knew we were talking about a counterclockwise rotation. Of course, rotations don't stretch anything. Rotations are rigid motions, right? there's no area magnification happening with the rotation. So we'd better get 1 as our answer. Now, I emphasize, you'll notice I have it written here, this is, again, expected. This is what it better be. After all, we understand that geometry, right? Nevertheless, in this course, I want to see the calculation. I'm just being, transparent about what we're interested in when we have questions like this. One of the big points that I'm looking for is demonstration of understanding of how to compute a stretching factor, and so I do want to see the work. Okay. All right. Okay, so now it's all over but the shouting. Let's see here. We do have this original integrand. And, of course, that's just a matter of plugging in. Again, we already know stuff like x is that. And so that x right there is that formula right there. Likewise, y is that dot product. And so this y is that right there. So that's just plugging in. Don't forget the stretching factor, right? So easy to forget the stretching factor. Our stretching factor, well, we don't forget the absolute values, which doesn't actually change the value here to 1. That's positive, so no worries. All right. And now again, we have ourselves a new integral. So your options, if you're interested in computing this integral on this domain, you can alternatively compute this integral on that domain, and again, don't fall for the distraction of, hey, I like that integrand a little better in the original integral, right? I mean, I guess it's a little better, barely, right? But look how much uglier the domain is. That's going to be 3 separate calculations because you're hitting 2 corners in the interior. The green integral, single calculation. Constant bounds, gotta love that. Much more desirable. Yes?
I just want to clarify, what the absolute value, does and does not, when we're allowed to put it, so...
It's part of the formula for the stretching factor, right? So stretching factor is specifically the absolute value.
Oh, okay.
Yeah.
And the reason you don't calculate directly I guess, because earlier you said you don't want to put the absolute value yet.
Well, the reason I didn't put it in initially is just kind of, it's a lot to carry that absolute value all the way through the calculation when I can just compute the Jacobian determinant first, and then at the end remind myself, the stretching factor is not quite the same as the Jacobian determinant. The stretching factor is the absolute value, and then you put that in at the end. Just make sure you put it in an honest way. What you can't do, and I do see the following a lot, is I'll see something like students will compute the determinant of and again there's the alternative notation. This determinant equals, and they'll compute blah, 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 and they'll get -3, and then they'll say equals absolute value of -3 equals 3. This is a major math crime. Massive. Oh my God. That is absolutely not true. Right? Please don't do that. Did everybody see why? It's plain old dishonest. It's factually wrong. It's not even close. Right? Equals are not commas. Right? So anyway, as long as you don't do that. Does that make sense? Yeah. Right. Okay. Okay, now a couple little details that just have to get said, and this isn't going to be something we're going to worry about so much in this course, but technically you do need for your change of variables function to be continuously differentiable, otherwise things don't work. 2 seconds. And we also need it to be invertible. Again, we're not going to encounter any such problems, but I just wanted that on record. Yes?
Okay, going back to what you just said, so like in the previous example, you flipped around the signs, the absolute value of the 4UV minus 9 was 9 minus 4UV.
Yep.
Do you only do that if When do you change it to negative
So,
versus
yeah, no, don't think of it as a rule for when you just throw in minus signs arbitrarily. It's just not a good way to think about things, right? What I'm doing here is I'm invoking a theorem that says that if you have a negative number, then the absolute value of that negative number is the negative of that number. Now, this isn't so hard to see why it's true, right? But that's all I'm doing, right? And so this theorem, 4uv minus 9, this is something that I have indeed established is negative, and therefore its absolute value is its own negative. Is that satisfying?
Yes.
Yeah.
So then, for the next example, like with 1, obviously that's just 1, so you wouldn't change it.
Yeah, that's right. I put this in. I put in the sort of the. I indicated that there's an absolute value just in case. Conceivably, I could imagine, and this isn't even an outrageous speculation. But keep in mind, graders are looking for proficiency. They're not looking for answers. Students have had it drilled into their heads since kindergarten that if you get the right answer, it's all cool. And that's absolutely not true. Right? So the fact that I don't need to in terms of getting the answer is really not the point, right? What I've accomplished by putting this in here is I have unambiguously communicated to the grader that I know that stretching factors are absolute values of what I actually computed. Does that make sense? So it's a clarity thing, right? And so it's a... there's a kind of a mindset shift that you have to kind of unlearn all the horrible implicit lessons that I assume. I certainly did when I was coming up in grade school. I got implicitly taught all these bad lessons, and you have to kind of try to resist. Yeah. All righty. Let's move it along. Here's a neat observation. It is sometimes beneficial to think of the transformation going the other direction. Now, why that would be will reveal itself in the next example. So for the moment, let me accept that sometimes we need our change of variables function to go backwards. If we do, let me remind you, when it's going the direction we're accustomed to, not that it's right or wrong. Right? The stretching factor comes from looking at the output variables, partials, with respect to the input variables. It's not about right versus left. It's about output versus input. Right? So if I turn this around, if I were to imagine what if I was going to view this as my change of variables functions? Well, now my outputs are u and v. Left and right doesn't matter. The point is I'm looking at a function whose outputs are u and v, and I would need to take its partials with respect to its inputs, which are x and y. So just by way of our existing convention for how to write the stretching factor, for this function, this is how I should write the stretching factor. And again, now keep in mind, these stretching factors, we write them as if they're fractions. They are not fractions. They are determinants. It's a shorthand notation for a determinant, right? So I can't just say, it behaves like a fraction because I chose a notation that makes it look like a fraction. That's nonsense. But here's the good news. They do behave like fractions. And in this case, the way we see that is to observe that, look, whatever little piece of area I might have over here, I know what happens to that when I look at its image over on the right, and I also know what happens to that when I apply the inverse function going the other way, and altogether, this is a two-step process, right? Where I first multiplied by that purple stretching factor, and then subsequently I multiplied by this dark blue stretching factor, and altogether, nothing happened. Altogether, I got the exact same area back. Altogether, the combined stretching factor has to be 1. And so therefore, these numbers are reciprocals of each other, and they behave like fractions. Right? It's a really nice little observation, clever little construction to get what we want. Now, why would we care about that? Comes up in this next example, and this is tricky. This is one of these examples, by the way, that I never would have thought of this probably if someone hadn't shown me. It's a tricky move. Please don't get intimidated by the idea of, oh man, I never would have thought of that. Which happened to me a lot when I was in college. That's why I dwell on it. Okay, so here's the idea. Suppose your domain, and by the way, this happens more often than you would think. Suppose your domain is bounded by 4 curves, 2 of which are level sets of one function, and the other 2 of which are level sets of a different function. So that's what we're looking at here. We have 4 equations, more to the point, 2 pairs of equations, both of which are level sets. And again, this comes up surprisingly often. So, if this is my domain, then I'm trying to do an integral on this region. That's a pretty crazy looking region, and you can think in terms of how you would slice that up, and notice whichever way you slice, you're hitting corners. 2 of them. This is going to be 3 separate integrals. 3 separate iterated integrals where the bounds are not constants. There's going to be reciprocals in the bounds. When you solve for x or y in these equations, reciprocals. It's weird. Pretty undesirable. Okay, so here's the clever move. Here's the insightful, I never would have thought of this if someone hadn't shown me. But someone did, so I can now do it, and now I'm telling you, and so very soon you're going to be able to do this. Here's the idea. Take your pairs of curves, right, and write their equations as level sets. Now, in this case, they came to me as level sets. If they have not come to you as level sets, do whatever little algebraic manipulations you need to make them into level sets. Once you've gotten them written as level sets, whatever you're looking at level sets of, make those expressions, make those your formulas for a change of variables function. So you're going to call one of them u, you're going to call the other one v. Seems weird? That defines a change of variables function like so, and here's why this is awesome. It's not clear yet why this is awesome, but here's why. Let's just think through now what my new domain looks like, and I can think this through by looking at one curve at a time. If I look at that curve right there, for example, that curve is where xy is equal to 1. Okay, right, but but don't forget that xy is u. So if we're looking at a curve xy equals 1, I can rewrite that as u equals 1, which is a straight vertical line in my UV plane. Isn't that nice? Right, and then likewise for the others. These 4 wacky curves turn into 4 lovely lines parallel to coordinate axes, right? It's really nice. And so then I can conclude from that this highly undesirable domain that I was given turns instead into the dream, namely a rectangle over here in my new space. So that's why this trick this is why this is an awesome trick. Why, if you form your change of variables function in this way, when you find yourself in a scenario like this, you get a rectangular pullback. Okay. All right, now notice the function's going the wrong way. I'm Translation. It's going the way that's the opposite of what we're accustomed to, right? We're kind of accustomed to when you have an integral with a domain, you need to view that as that undesirable domain as being an image. That is not what we're looking at. It's not an image here. Here, the pullback domain is the image. So this function's kind of going backwards. Okay, well, we'll deal with that when we have to. I do know, however, that I'm going to need to compute the stretching factor. Now, of course, my outputs are u and v, so I'm going to compute the partials of the outputs that I have with respect to, of course, the input variables that I have. So I'll be taking the partials of u and v with respect to x and y. That's all I got. You compute that up, fine, and that gives you this formula. Wait a minute, though, that's not what I needed. Reminding ourselves that this is the integral I'm interested in. I want to rewrite that in terms of u and v, and now I have to ask the question, what is it that I would multiply here? What is the stretching factor that I need to insert? What is it that I'm going to multiply by du dv to get dx dy? Well, again, commit the math crime here, the victimless math crime. Pretend like those are going to cancel. Pretend like that's going to tell you what it turns into, and that just tells you which way you need this to go. Apparently, I need partial xy, partial uv. That's what I need to compute to make the pieces fit together. Yet what I computed over here, this xy squared, is the reciprocal of that. Right? Does everybody see the bind we're in? We computed the wrong one. Now, not our fault. Why did I compute the wrong one? I computed the only one that I could compute. Given the formulas I have, I don't have formulas for x and y. I have formulas for u and v. I computed what I could. I need the other one. I need the reciprocal, and so no problem. Take the reciprocal. Nothing to it. Is that cool? So I think this notation has done some great service for us. Writing that stretching factor as a fake fraction, writing this stretching factor as a fake fraction allows us to easily see whether I do or don't need to take the reciprocal. So, big fan. All right, and it's all kind of over at this point. You just we plug in what we just computed that. It's the reciprocal of xy squared. We had an original integrand. You combine, blah, 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 and here's your new integral. And the only bad news about this new integral, this is, whoa, what happened there? Oh my gosh, what's going on here? My pen just went crazy for a second. I'm in the UV plane. But notice the integrand is in terms of x and y. I need to plug in for x and y. I don't have formulas for x and y. That's the whole reason we got here in the first place. So I'm going to have to figure out how to rewrite this integrand. Currently in terms of x and y, I'm going to have to figure out how to rewrite this in terms of u and v. And whenever you sort of go backwards, the way the arrows are going, you're kind of always going to be painted into this little particular corner, unfortunately. So how do you do this conversion? How do I rewrite? Come here. There we go. How do I rewrite this in terms of u and v? This is what I want. Okay, what's the trick there? And it's less a trick and more of a strategy. The big idea is to take a guess of the form and then try to introduce some fudge factors and solve for the fudge factors, basically. So my speculation goes as follows. What I have is a product of powers of a product of powers of x and y. My u and my v themselves are Check it out right there. Products of powers of x and y. So my goal is to figure out how to take some products of powers of x and y and how to turn them into a different product of powers of x and y. And my best guess is how to relate these products of powers to a different product of powers is probably not going to involve cotangent. Right? It's probably going to be, now this is a guess, I can't prove it, but it's probably going to be a product of powers, isn't it? Because if you take a product of powers of products of powers, you're going to get a product of powers, which is what we want. Now this is just a guess, right? I mean, I don't know, I don't know that this is the right form. I'm just guessing. But it seems like an educated guess. It's a reasonable, plausible guess. And very often your reasonable, plausible guesses are going to work. So in this case, you just kind of multiply it out. And when you multiply everything out, you'll notice that you get that A plus B has to equal to 7. And you also get that A plus 2B apparently has to equal to 1. And so you need to figure out how to solve that little system of equations, linear algebra. Y'all are experts at that. And that gives you this, which gives you those numbers, which allows you to get rid of that, which allows you to rewrite. I painted myself into a color corner. The expression you're interested in that you speculated would take that form, you can rewrite then in terms of u and v. And that is what you stick into there. So it's algebra games. Everybody see how that worked? It's not always going to be like this, but this is the strategy that very often will give you what you need. Okay, let's see how we doing on. Okay, great. Okay, so where did this stretching factor formula come from in the first place? Recall, I didn't discuss this previously. We had a lot going on. We had a bunch of stuff to keep track of. I wanted to get some wins in the win column. We have several wins in the win column now. We've gotten our hands dirty. We've seen the mechanics of how to do change of variables. So let's go back now and worry about where the stretching factor formula came from. Recall, the big idea of the stretching factor is that some amount of area, du dv, in the UV plane is going to have to be stretched by some factor to make this amount of area, whatever that is, in the xy plane. I'm looking to compute that and have it be some scalar multiple of the green area. I just need to compute that scalar multiple. So I'm literally, what I'm going to do here is I'm going to compute dA. I'm going to compute that thing. I'm going to view it as being a multiple times du dv, and that's our stretching factor. Okay, now how do we do that? How do we compute this area? Well, this area comes from these edge vectors. Whatever those edge vectors are, those will be the columns of a matrix, and area of a parallelogram is the absolute value of the determinant of that matrix. That's just a callback to Chapter 1 and or linear algebra, depending. Right? So old news, in other words. How do I know that's what those edge vectors are? That's the sort of the next natural question. How do I know that this? Yeah, okay. How do I know that that vector is this formula? Well, recall that's an easy vector to write down. That green vector, its magnitude is du. It's pointing in the E1 direction. That's just a easy little construction. I know its direction. I know its magnitude. I can write it down as a vector. And remember, furthermore, that the derivative matrix is what turns input vectors into output vectors. So knowing what I have on the left, multiplication by dg gives me what I have on the right. All right? So there you go. And then there's just a couple of little details to bang out. Now that we have this formula, I will notice that there is a scalar factor right there. Scalar factors just come right on out. Here's another scalar factor. Scalar factors, again, they come right on out. That was convenient. That leaves us then only with the need to compute whatever this is. What is this matrix whose first column is the product of the blah blah and the second column with how do I simplify all that? And that's plug and chug. And this is something you can do yourselves. I encourage you to take the minute or so that it'll take you to do this. If you just write down explicitly what dg is, then explicitly multiply by E1 and E2, then explicitly make these columns as indicated, what you will find is that the result is exactly dg. Happy little conclusion, as it turns out. And so we win. Everybody good? Okay, what if we're in 3 dimensions? The story in 3 dimensions is the same, except 3-dimensional instead of 2. It's so the same. Suppose we find ourselves looking at an integral over some nightmare of a domain like this horrifying thing right there. And let's just take a moment just for the fun of it all to speculate on how much of a nightmare that domain is. Right? Oh my God. Whichever direction you slice, well, there's a total of 8 corners, and there's going to be a first one, there's going to be a last one, and there's going to be 6 corners in the middle that you're going to slice through, whichever way you slice. By the way, then further, each one of those slices, and I'll take a whack at drawing this. Oh gosh, I hope I can do this. That slice that you would get itself is not a rectangle, is it? So as you slice that up with respect to whichever way you go, you got 2 options. Yeah, well, you're going to hit a couple of corners and possibly worse. So you're going to have 7 different integrals just from slicing in the one direction, and you would expect at least 3, possibly more, integrals for each one of those as you do your next slices. You're going to be looking at 20 or more separate iterated integrals, and a heck of an art challenge, right? So nobody wants to go down that road, right? Nightmare. All right. So, the big plan, just like with double integrals, we want to view that as being an image by way of some function, an image of a hopefully more desirable domain. Again, the dream is that it might be a rectangle, fingers crossed. And so all we really need to know is how much does volumes over here, how much do they get stretched out to become volumes over there? We're going to need a stretching factor, and good news, same formula, same shorthand notation, and ultimately, same reason. And I'm going to leave this as an exercise for you all. I think this is a really healthy exercise. If you want to check whether you understand this argument here, take all the time you need to look at this, digest it, make sure you totally get it, and then just try to copycat it in this scenario here. It's totally going to work out. And again, you're always welcome if you get stuck on this and you're not sure how to proceed on doing that derivation. Come to office hours. I'll be very happy to walk you through it. Okay, so same deal. Before I show you an example, I have a quick little theorem I want to state. This is another one that y'all can directly check this for yourselves. There's nothing to it. Very straightforward confirmation. But if you have a linear transformation that you use as your change of variables function, whatever matrix represents that linear transformation, that matrix is also the derivative matrix for that change of variables function. Again, easily confirmed. Just write down a matrix A, give it some entries, A, B, C, D, E, F, G, H, I, whatever, right? And write out the formula for T, compute its derivative matrix. Notice it's exactly A. Very straightforward. Take you 3 minutes, worth your time. Okay, so that noted. Now let's look at our example. This is another really clever trick. Don't ask yourself, would you have thought of this on your own? Doesn't matter. You don't have to think of it on your own. I'm showing you the trick here. The goal that we're going to be addressing is, suppose I'm interested in doing some integral over a parallelepiped, specifically a parallelepiped that's defined by 3 edge vectors and a corner at the origin. Let's again take a moment just for fun and think about what a nightmare it would be to slice that up the old-fashioned way. You're hitting corners all over the place. You're getting all sorts of weird shapes. Oh my God, right? Non-starter. Let's not. How am I going to compute an integral over that domain? And again, not a rare circumstance. Parallelepipeds are all over the place, right? So how do I compute an integral on this perfectly plausible but highly undesirable domain? All right, well, I want to find a clever way to view it as an image. And it turns out, here's the clever move. I don't know if I ever would have thought of this on my own, but what I was shown and now you are shown, here's the trick. Take the 3 vectors, make those the columns of a matrix, and make your linear transformation just be the linear transformation that comes from that matrix. That's it. That's the move. If you're looking at a parallelepiped, take the edge vectors, make those the columns of your matrix. Now, why does that work? Okay, well, because if I were to look at standard basis vectors over here, now what does, I've constructed a linear transformation. Let's ask for fun, what does the linear transformation do to my standard basis vector here? Well, I would be multiplying my matrix times a standard basis vector. And fundamental fact number 1, arguably, in linear algebra, is that a matrix times a standard basis vector gives you the corresponding column, which means that my edge of my unit cube becomes the corresponding edge of my parallelepiped, and if the edges go to the edges, then the cube goes to the parallelepiped. So that's why it works. Everybody see how that argument makes sense? Everybody see, therefore, how to, in this case, and again, every scenario is different, but again, tools in your toolbox. In this kind of a scenario, that's the move. I wish I'd thought of it. Okay. All right, so, doing so, a lot to erase here. Not much to it remaining. I take my dx, dy, dz of the integral I was given. That's going to be stretching factor times du, dv, dw of the new integral that I want to turn it into. That's stretching factor per this theorem up here. Determinant of the derivative matrix means I just need to take the determinant of the matrix defining the transformation in the first place. So this is just the determinant of that matrix. We're basically done. The one last little twist is don't forget where your output coordinates come from. So in particular, what is z? this z right there, how do I compute z? Well, it's the third output coordinate. And just to be explicit, this formula right here says that the matrix A times UVW is XYZ, and so the Z that I'm looking for is just the third output coordinate. So multiply, look at the third coordinate, and you're going to find that it is this right here. Everybody happy? This may be the best example that we have because it turned a nightmare of 20 or more necessary iterated integrals instead into a single one over, again, the dream domain. Nothing to it. Yeah.
So you don't have where is the stretching factor multiplied?
Oh yeah, it's right here. So that's my stretching factor.
Okay.
Yeah, that's what I inserted. That's what turns output area into stretching factor times input area.
Okay.
Yep. Okay, so that's pretty much change of variables. Now, that's about a third of the section. Oh my gosh! So the next topic really should be its own section, in my opinion. But whatever, it doesn't matter. And that is basically a special case of change of variables. And it's a really nice special case, a really important special case. It turns out that anytime you look at a coordinate system, that coordinate system can be viewed as a change of variables function. It's a little surprising, but remember, this is the point of view I was pushing on polar coordinates. A lot of people like to think of polar coordinates as sort of geometry in the XY plane. That's fine, whatever. Right? But you can think of it as being a function, and take a look. That function has x and y as the outputs, and new variables. They're not u and v, they're r and theta. But whatever, two new variables is the inputs. That's a change of variables function. Likewise, cylindrical coordinates, again, thought of as a function, is a 3D change of variables function. Spherical coordinates, same. They're different, right? But they are all change of variables functions. And you can compute their stretching factors, and everybody should do this once in their lives. And I've done mine. Right, so I want you all to do this for yourselves. That calculation right there, computing the polar coordinates change of variables stretching factor, is not a hard calculation. You write down a couple of easy partials. You take a quick determinant. You'll notice the Pythagorean identity shows up. The answers are nothing to it. Likewise, cylindrical coordinates. Nothing to it. Now, that's a 3 by 3 at this point, but there's several zeros in that resulting matrix, and it's not bad. It'll take you a minute or a minute and a half. So a good thing to write down. Make sure you do that. And the last one, I'm sorry to report, is not as easy. But again, it's a healthy exercise. Everybody should do it once in their lives. It's your turn. So this will take you several minutes. This is 10 minutes. Something like that. And it gets a little hairy. And it gets a little ugly. And then Pythagorean identity to the rescue. The Pythagorean identity will take this massive matrix chock full of trig, the determinant, which will be this expression that will go several lines across your paper, right? And we'll simplify it into a nice, simple little formula there, rho squared sine phi. So again, I think everyone should do all three of these calculations. The first two are quickies, the last one is not, but it's a healthy exercise. By the way, just for your reference, I did one time, years and years ago, make this calculation an exam question. So anyway, for whatever that's worth, interpret from that as you will. It's not a threat. Right, but I think it shows how the extent to which I think it's important to do. Okay, now back up to this. What are we going to do about this absolute value? After all, the absolute value is what the stretching factor is. We've computed the thing on the inside. We have not dealt with the absolute values. Okay, well, I'm sorry, the absolute values are there. It's part of the deal. That's what the stretching factor is. Right. Okay, so here's how we get around that annoyance. We do have this polar coordinates deal that we've set up, and I emphasized at that time there is no rule indicating that R has to be positive, and it remains. There is no rule requiring that R should have to be positive. But there's also no rule saying that I can't choose personally. I make my personal promise when I'm using change of variables with polar coordinates. I promise I will always, right hand, I will always choose with my free will positive values of R only. Only positive values of R. And when I make that promise that I will never choose any negative values of R, in that case, now we're taking the absolute value of an established positive, or at least non-negative value, and therefore I can lose the absolute values. Yes?
What does SF stand for?
Stretching factor. Yeah, that's my little pencil saver. Yeah. So it's not that you have to, it's that you may. And I strongly encourage that you should make a similar promise, right? Always choose only positive values of R. And you got to keep yourself honest on that. You got to check. You got to think it through. Make sure that you don't accidentally set things up where R is negative, because then you catastrophic problems, right? You would have the wrong stretching factor. You'd get some cancellations that shouldn't have happened. You get dramatically wrong answers. So do keep yourself honest on that. But if you do, then boom, stretching factor, no absolute values. There it is. Handy deal. So we make a similar promise for cylindrical coordinates. Not that I have to, but that I choose to always use only positive values of R, and then again, stretching factor simplifies similarly. And here's where a lot of people mess up. A lot of people figure in polar coordinates, R is what I have to make positive? Okay. In cylindrical coordinates, R is what I have to make positive? Oh, okay. Well, then in spherical coordinates, probably rho. Right? Seems like the analogous thing must be rho that I would have to promise to be positive. And that doesn't help at all. Right? If you look at this expression for your Jacobian determinant, what happens? What's the benefit if you promise to make rho always positive? Doesn't help at all. It was going to get squared anyway. Right? So very common misunderstanding for students to think that, I hereby promise that I'm going to make rho always positive. Useless. Make rho negative all you want. Doesn't matter. Really doesn't. Right? What you have to be careful about instead, you have to be careful that sine phi always be positive. And so I'm going to choose these values of phi. I'm going to promise that I will only, when I'm doing spherical coordinate integrals, I'm going to only use phis that are between 0 and pi. And if I make that promise, well then again, good news. That means that this will be positive. And this is, of course, obviously positive. I don't need any help with that. And then, therefore, this is positive, and therefore I can lose the absolute values, and my stretching factor becomes easier. All good? All right, so let's see one in action. So let's consider this integral on this domain. Let's take a moment to recognize how bad that would be if I do this brute force. Now, no corners. That's nice, right? But as I go through my slicing process and as I solve for y as a function of x at points like this, as I've done my slices, in order to get my upper bound, notice solving for y as a function of x, I get a square root. Now I've got a square root in my inside bounds, which means I'm going to have square roots in my outside integrands, and I don't like square roots in my integrands. Yeah? Okay, so undesirable, not happy. Okay, neat observation, using polar coordinates. This domain is an easy image of a rectangle. Right into it. We'll walk through. Let's see how that works. Let's think about the edges here. What's going on with let's say here this edge right there? What's happening on that edge? Well, that edge, you'll notice very quickly, has r equal to 1. Okay, r equals 1, and then apparently theta goes from 0 to pi over 2. So let's do that now in the xy plane with r equal to 1 and theta going from 0 to pi over 2. That just makes that edge right there. And then you can kind of continue on around. This edge, theta is pi over 2. R goes from 0 to 1. Boop, it's that. Likewise, let's see here. This edge, theta is 0. R goes from 0 to 1 is that. And then the weird one, this is a little weird, but that edge is where r equals 0. That whole edge gets kind of pinched down to just this point right here. And so, yeah, there's some sort of a smushing kind of this kind of a motion here, sort of pinching on the left side there. But nevertheless, this domain over here, its image is, I ran out of colors, this domain over here. And as desired, my undesirable domain is an image. And I can just do a pullback, wave the magic wand that says change of variables, insert the stretching factor. Boom. Is that cool? Let's go through those details a little bit. Don't forget your stretching factor. There it is. No absolute value necessary. Let's double check ourselves. Did I follow my rule? Did I stick with only positive, or at least non-negative, values of r? Why, yes, I did. So that's all good. Let's see here. I'm going to have to do the algebra to convert, and how do I plug in for x and y? And you can plug in the x and the y directly. X is r cosine theta. Y is r sine theta. You can plug that in and do some trig, or you can just recall that we have an existing rule that x squared plus y squared is r squared. We've done the pullback. Here's my new domain, as previously discussed. Here's my new integrand. Don't forget your stretching factor. Your stretching factor is part of your new integrand. So my new integrand there is just r cubed. My bounds are constants over a rectangle. Life is good, easy computation, and this is no sweat. Yeah.
So the new bounds in the polar coordinates, were those bounds solved? Did you geometrically kind of see them, like see through the original like XY bounds, and then kind of they look?
Well, what I did here, I'm going to give you a different point of view on this in a minute, but for the moment, the point of view I'm taking is that one edge at a time, I can see that my new domain maps straight on, like this maps straight onto that, right? And then likewise around the rectangle, and then therefore what's inside goes to what's inside. So, but there is a different point of view I'm going to give in just a moment. Yeah. Okay. So, nice little takeaway here is that for, in fact, fairly common shapes, right? Using the polar coordinates conversion formulas as a change of variables function, it's pretty cool, right? It's very handy in the case that we just saw, and it is handy, I claim, in many cases that arise very regularly. So very, very, very valuable to make sure that you are comfortable with using this as a change of variables function, and make sure to memorize that formula for the stretching factor, and of course this requirement to make that legal. All right, now here's a neat observation. We can streamline this process in a very handy way by making a couple of innocent observations. Let's think about what theta slices look like, and of course a slice means constant value of that variable, and so perpendicular to that axis, this is what a theta slice looks like. And of course there are various theta slices. Whatever constant value of theta you pick. Well, here's the thing. A constant value of theta, I know what that looks like in the xy plane as well. That ray coming out of the origin right there, that too represents a constant value of theta, this time seeing it in the xy plane. And various different constant values of theta just give you various different slices that look like that. That's just an observation. So, going back up to what we did here, when I was writing down these bounds, what I was doing, of course, is looking at the various different theta slices, and here's what those theta slices looked like. And yeah, I can see them over there in our theta space, but I can also see them over here in XY space. There they are. That's the same slices, just seeing them in how they look in the XY world instead of how they look in our theta world. And you can make a similar observation about R slices. R slices just mean constant values of R, and I know what that looks like in XY world. So here's the wonderful punchline to this, the really nice upshot. Even though I am in fact doing a change of variables here, even though, yes, there is a pullback domain, even though, yes, I'm going to have to slice up that pullback domain, I don't really actually have to write any of that down. I don't have to draw the pullback. Everything that I need I can see right here in my original picture. You just have to remember what slices look like. Right? So really, really convenient. Rather than try to draw the pullback, I'm just going to see my theta slices. There's my first theta slice. That's apparently where theta is 0. And then here are subsequent theta slices. And it would seem that I stop when I get to pi over 2. It's the same conclusions I would have had over there, but I don't need to see it over there. Doing business in the r theta plane is an artistic requirement. It's more that I have to draw. And why put yourself in a situation where you're drawing stuff you don't need to draw, right? So you can see your bounds right there. Let's see here. Let me get rid of all that. So yeah, from this right here, you can see that your theta is going to go from 0 to pi over 2, and then you can fix a value of theta. If I can find my little button, there it is. We're going to fix a value of theta. And now let's think about what happens to r. Well, apparently we start right there where it's pretty clear. r is 0. And clearly we're going to end when we get to here on the unit circle, which is the boundary of the unit disk, which, part of our deal, where r is clearly 1. No pullback picture. Now, I emphasize, we are still doing a pullback. There is still a new pullback domain. I am still slicing in the usual way on my pullback domain. I'm just choosing to kind of cheat and pull the minimal data that I need from that pullback slicing. I can see that data that I need in my existing picture. This is just a hack workaround to save you drawing extra stuff. Super handy. And so this is a very common point of view to take. This is called doing the integral in polar coordinates. That's just code for I'm doing a pullback, but I don't want to draw the picture, so let's see it all here. Yes?
Since the pullback doing is rectangular, can we switch the DRT data when we're doing
Yes, that's right. In this case, you can because the pullback is rectangular. Yes, absolutely. Yeah, in this context, it might be slightly more streamlined to observe because the bounds are constants. And then you don't have to make a reference to something you haven't drawn yet. But it's true, whenever your bounds are constants, you can always do this. Yeah, totally. Good question, yeah. Everybody happy? Okay. Oh, shoot. Okay, oh, gosh. Yeah, okay. We're out of time. We'll draw the line right there. Pick up here tomorrow. Y'all have a good rest of your Wednesday. See ya. Oops.